everybody, very warm welcome to Vedantu JEE English channel, and today we are starting with a one shot for class 12 and the chapter name is of course the solid state. So how are you all doing? Yes, I hope that you all are doing great, and let's start with the chapter. What do you all say? Without much further ado. This is what I think one of my tagline. Anyway, so in today's chapter, obviously, we are going to complete the entire chapter, everything and anything. Yes, now I understand that this chapter has been deleted from your boards, but it is a part of JEE Mains and JEE Advanced. Yes, so please don't think that because this chapter is not there in your rationalized content, you don't have to study. Not at all. Yes, it's a myth if you're still thinking like that. Anyway, so solid state, when we say the solid state, when we say this whole sentence, solid state, you understand that in your class 11th, you have studied about something called as states of matter, right? And in states of matter, we studied about solid, liquid and gas. And we know that in solid, it has fixed shape, fixed volume. So that solid part is what we are going to study, okay? Liquid, you all know that, liquids don't have a fixed shape. They take the shape of the container, right? They have fixed volume. And gases, they do not have shape, no fixed shape. They do not have fixed volume either. However, in today's session, we are going to focus more on the solid state, okay? All right. So while we are at it, let's take a look at the characteristic or the properties of solids a little more, right? And if you look around, you will find a lot of different types of solid. For example, right now I have this cup. This cup is solid, right? I have my green tea in this, isn't it? I drank a little bit of green tea. Apart from this, if you notice my mobile phone here, this is also solid. Yes, the AC remote is solid. I also have a chair. I also have a desktop. I have many things around and most of them are solid. So whenever we take a look at solid, right, what is it that we see? We see that they have definite mass. If I pick up the chair, let me pick up the chair and show you. See, if I pick up the chair, it does have a definite mass, isn't it? Of course it does, yeah. It was a little heavy for me to carry it by only one hand. Also, it's very tall, almost my height. So definite mass it has. It has definite volume and it also has a definite shape. I can't just change the shape of the chair just like that, right? It will ask me to become the Incredible Hulk if I have to change the shape of the chair, correct? Yes. Then we understand that intermolecular distances are short. What do we mean by this? Let's understand this, my dear student. Intermolecular distances are short. So if I have to make the atoms or the constituent particles basically means the particles that make up the solid. So the particles can be atoms, the particles can be molecules, the particles can be ions, right? Yeah, constituent particles can be anything. So basically, if I make up these constituent particles, I'll make something like this. Yes, I'll make it like this, correct? Right? And we all know that the intermolecular, see this distance, this molecule, between these two molecules, do you see that the distance is very small? And that is exactly what we mean when we are saying that the intermolecular distances are short. Okay? All right? Yes? Now we are saying that the intermolecular forces are strong. What are these intermolecular forces, bacha? Yes? The intermolecular forces are basically, yes, it is basically the attractive or the repulsive force. What do we say? Sorry, my sweater is making it a little difficult for me to write because that was touching the board. Anyway, so the attractive or the repulsive force, the attractive or the repulsive force between the constituent particles. Are called intermolecular forces. Oops. are called intermolecular forces. All right, yes, okay. So the intermolecular forces are very strong, which is why it is very tough when you want to break a solid, okay. You cannot break solids very easily. Why so? Because the intermolecular forces, yes, the force with which these two molecules are attracting each other, they are keeping them together. They don't allow them to break, okay. Their constituent particles, they have fixed positions, yes, and they can only oscillate about the main position. Did you see the first picture? Yes, see, they are vibrating, they are moving, but they have only one single point. Yes, they have a mean position with respect to which they are vibrating, they are oscillating. Oscillation is what? Oscillation is basically to and fro, to and fro. Oscillation can be called as vibration too. Oscillation and vibration, there is not much difference, okay. I mean, however, you probably do learn about it in physics a little more, so I am not the best person to comment about it, okay. Yes, and they are incompressible, you cannot compress them, and they are rigid, obviously, because they are incompressible, they are rigid, you can't break them apart as well, okay. Now moving on, classification of solids. Solids can be now classified into two big groups, okay. That means that we can broadly classify solids into crystalline solids and amorphous solid. Now do you see that I have given a very cryptic image here? For crystalline solids, do you see that there is a very long Q here? Yes, a very long Q. Q, you understand? Q, U, E, U, E, a line. There is a very long line here. Do you see? And when it comes to amorphous solid, do you see that how people are, standing in a very disorderly fashion? There is no order here. Do you see any order here? There is no order here, right? People are just standing like this. However, we will come to it, but just remember this picture, okay? Now, crystalline solids, when we talk about the atoms, the molecules or the ions, they have an ordered arrangement. See, order arrangement, how they are standing in a line is very ordered, right? They are following a certain discipline when they are standing in the queue. However, in here, you don't see that order, right? That's exactly what we mean. So, in case of crystalline solids, the atoms, the molecules or the ions, they have an ordered arrangement which extends over a long range. Yeah, alright. Whereas when it comes to amorphous solids, constituent particles are randomly arranged. Okay, constituent particles are randomly arranged and they have no ordered long range structure. Why? See, there may be a queue. If you just take a look at this part, yes, there are people who are standing. There are people who are standing in a queue right here, but after that you do not see any order. So there is no long range order, maybe, but for a very short time. Only maybe 2 people are standing in a line. Only 4 people are standing in a line, but after that there is no order. After that everybody is just haphazard, wherever they want to stand, they are standing. You get my point? Yes, makes sense, nonsense? Great. Okay. Alrighty then. Alrighty. Now let's take a look at the difference in the properties of crystalline and amorphous solid. Okay. So when we talk about the properties, we are going to talk about the shape. What is the shape of a crystalline solid? They will have a definite geometric shape. Yes, they will always have a definite geometric shape. Whereas in case of amorphous solid, we will not see that. We will see irregular. Yes, the shape can be anything. Okay, the shape can be anything. When we take a look at the melting point, they have the crystalline solids, they have a particular point, they have a particular temperature, very sharp particular temperature at which they will melt. Whereas in case of amorphous, you see that over the time what happens is they just keep getting soften up. They gradually soften over a large range of temperature, right? They don't have a sharp melting point. It's not like at 100 degree they will melt. No. They start, they start softening over from, from 60 degree onwards, they will keep getting soften, and then, they will keep just melting, okay? Whereas in case of crystalline, you have a particular temperature at which they melt, okay? Yes, then there is a cleavage property. So when you cut them with a sharp knife, what will you see? You will see new surface, which is absolutely plain and smooth surface. It is shining, right? Mostly have you seen in case of metals? Like let's say that you take an iron nail which has been outside for a very long time. So it has got some rust. Yes, it has got some rust. But if you cut that iron nail into two parts, you will see that the inside of the iron nail is still shining. It's still shining, okay? But here what happens is when you cut it with a knife, it forms two pieces, but it still has irregular surfaces. For example, tell me something. Have you seen a glass breaking? When a glass breaks, it can be very sharp, right? And everything is very disordered. It doesn't break into exactly two single pieces, exactly very similar two pieces. Does it break like that? Nah. It breaks into very weird shapes, and then some of them can even cut you, right? Exactly, understanding? Now we come to heat of fusion. What is heat of fusion? Definite characteristic heat of fusion. That is, when you are boiling them, they will have a particular boiling point as well. Whereas in case of amorphous solid, you will not even see that, okay? They do not have definite heat of fusion. Arrangement of constituent particles, they have long range order. What is long range order? Did you see how they form this line? Yes, for a very long time they are following order. See, from here to here, at least 20 people are standing in the queue and all of them are following an order. So 20 is a long range, isn't it? Exactly. So they have long range order, whereas you don't see that in the amorphous solids. In the amorphous solids, you only get to see short range order. That is, the order is followed only in very short. Yes, order is only followed for very short duration or very short range. Okay, all right. Yes. Then comes anisotropy. So crystalline solids are anisotropic in nature, amorphous solids are isotropic in nature. That we will understand. Don't worry. It could be new words for you, but you will understand. Don't worry about it. Nature. Crystalline solids are called true solids, whereas amorphous solids are called pseudo solids. Have you noticed one thing? Your glass windows, right? If your glass window is there, measure the top part of the glass, the thickness of the top part of the glass window and the bottom part of the glass window. You will see that after a certain point of time, the bottom part of the glass window, the thickness starts increasing and the top part has, thickness reduced. Why? Because at certain point it starts to flow very slowly, but it does flow, which is why we call them pseudo solids or cooled liquids. Okay, what do we call them? We call them as pseudo solids or cooled liquids. Get my point? Yes. Now let's understand what is this anisotropic and isotropic. Okay, you see these pictures? This is basically what is anisotropy and isotropic. Okay, so let me write it down here. This is for anisotropy. This is anisotropy and this is isotropy. But the question is, what really is this, right? We still haven't understood that. What exactly is this? So when you measure physical measurements, when you measure the physical properties, right? Yes, you measure physical properties, isn't it? Physical properties there are many physical properties, right? Physical properties is hardness, physical properties is appearance, physical properties, refractive index is a physical property. So these are all physical properties. So when you measure the physical property, you see that in case of anisotropy, it's not the same in all direction. What is it? It's not the same in all direction. But in case of isotropy, if you directly, if you just want to find the meaning of this name, isotropy, and if you exactly same like this, as it is, if you try to convert it into simple language, iso means same, tropy means direction. What did I say? I said that iso means same and tropy means direction. Tropy means direction. Okay, all right. So let us write that down here. Let us write that down. What did I say? Anisotropy is basically physical property. Measurement of physical property are not same along all directions. Okay. Yes. Measurement of, did I not change the color? I thought I did. Why did it not change? I want to change the color and write. 1 second, guys. Yeah. Measurement of physical properties are not same along all directions. Cool? Alright everybody? Yes. But in case of isotropy, the literal meaning is same direction. That means that the measurement of physical properties are same along all directions. Yes. So what do we write? We write here that measurements of physical properties are same along all directions. All right, get it? Okay, this is the difference. Now see, what I meant when I said that measurements not same along all directions and same along all directions. See, this is your crystalline solid. So do you see that when you have this axis, right, the A and B axis? Yes, in the A and B axis, see, it's not same. Here you only see B, 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 B. Here you only see blue, 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 blue. Here you only see red, red, red. Not similar, right? Not similar. The constituent particles are not similar in both the sides. Now when I draw this axis, C and D axis, once again, do you see that here you have 1, 2, 3, 4, 5, 6, 7, 8. 8 constituents particle. Here you have 1, 2, 3, 4, 5, 6, 7. 7 constituent particles. Once again, not same. But in case of the amorphous ones, yes, isotropic, right? Okay, let us write this down also. Isotropic. Who are isotropic? Amorphous solids are isotropic. All right. Whereas an isotropic, who are anisotropic? The crystalline solids are anisotropic. Now you might still itch your head that but ma'am, crystalline solids are the ones that are following order, right? Crystalline solids, they have long range order. Then how come you are saying that they don't follow order? Exactly my point. Yes, because they are following long range order. If you cut them, if you divide them with axis, you will see that they don't have the same properties. Yes, they are not following the same measurements. In case of these amorphous solids, they are so random that whichever axis you take, whatever you measure, you will always find the haphazard movement. You will always find chaos, which is why it doesn't matter. But you will say that, yeah, the same disorder is followed. Basically, same disorder is followed. You understanding my point? Yes, yes, same disorder is followed. For example, see, okay, now we know that in the North India there is flood, right? So obviously the flood in Delhi would be different from the flood in Himachal. But for people who are sitting here in Bangalore, I see that, oh, flood, there is flood. Overall in India there is flood, right? So for me, from this perspective, I am saying that is the same disorder. Of course it is different. Of course it is different. The flood stories of people who are in Himachal and the flood stories of people who are in Delhi, it is different. But when I look at it, I feel like, oh, it is the same. They are losing out on property. They are losing lives. Yes. Are you understanding this? So that is your anisotropic and isotropic difference. Okay. All right. Now we come to another property, that is your cooling curve. Okay. What is this cooling curve? Basically, when they are cooling, the solids are getting cool and we make a curve out of it. So temperature and time. Okay. So what do? We make a curve, isn't it? So we make a curve here. Yes, this is our first curve. Okay, this is time here. And this is your temperature. So when we draw the curve here, we see that for amorphous, it's a very smooth curve. Okay, for amorphous solids, it is a very smooth curve. All right. Yes. Now when I draw the curve for your crystalline solids, what happens is same, right? I will take time in the x-axis, yes, and I take temperature in the y-axis. So what I see is that there is a sharp 2 points I see here, okay. I see 2 points here, very sharp 2 points I see. Why? During crystallization, the temperature remains constant. At this point, right? At this point, what happens is, at this point, the temperature remains constant. Why? Because whatever heat they are gathering, they are utilizing it for crystallization. Whatever heat they are reducing, whatever heat they are releasing, they are now what? They are doing what? They are not releasing the heat. They are keeping it so that they can turn it into crystal. They are cooling down, temperature is reducing. So when you are cooling down something, when you are cooling an object down, the object is releasing heat, right? Object is releasing heat. Now what is happening is, for that certain period, they don't want to release the heat. They want to keep it so that they can use it for crystallization. They are using the energy for crystallization, okay? All right. So during the crystallization, at this point, the temperature remains constant for just a little bit of time, okay? All right. Yes. Now, crystalline solids, it is seen that they are more stable than amorphous solids. So let's just write it down that here is a point, okay? Crystalline solids are more stable all right. Yes, crystalline solids are more stable than amorphous solid. Now, shall we solve a question? Let's solve a question. It's a very easy question. So, which of the following is not a crystalline solid? Tell me. You gotta tell me. What is the answer? Is it table salt? Table salt is basically what? Table salt is nothing but your NaCl, isn't it? Yes. And plastic. What is the answer? Of course, the answer is this. Yes, this is an ionic solid. We will be reading about ionic solid also in some time, just in a little bit of time. Yes, this is your ionic solid, and plastic is what? It's not a crystalline solid, okay? It is not a crystalline solid. What is it? That means that this is amorphous solid. All right, bacha. All right, bachos. This is your amorphous solid. Understanding, no, bachos? Great. Okay. Moving on, next question. Which type of solids are isotropic in nature? We just read about it. Yes, absolutely correct. It is amorphous. Amorphous solids are isotropic in nature, whereas crystalline solids are anisotropic in nature. Once again, just so that you can remember it, I'm writing it down. Yes, that amorphous solids are isotropic in nature, whereas crystalline solids are anisotropic. Get my point? Yes? Okay. Moving on from here, next question for you is, amorphous solids are isotropic in nature while crystalline solids are anisotropic in nature. Explain. How will you explain it? You can always write that some of their physical properties like electrical resistance or refractive index, they show different values when you measure along different directions in the same crystal. Okay? And this arises because of different arrangement of particles in different directions. Yes. Now, since the arrangement of particles is different along different directions, the value of the same physical property is found to be different along each direction. Are you getting my point? Yes. Yes. Whereas that doesn't happen in case of amorphous solids. So let's write it down. Yes. For crystalline solids, what happens? Yes, some of their physical properties. All right. Some of their physical properties like electrical, what did I say? Electrical resistance. Yeah, that's what I said. Like electrical resistance, refractive index, yes, are found to be what? Yes, show different values, okay? Show different values. Different values when measured yes, when measured along different directions. Measured along different directions in the same crystal. Yes, all right. Which is why they are called as an isotropic. Yes, yes, all right everybody. Now amorphous solids on the other hand are isotropic in nature because there is no long range order only. Yes, so let's write it here. On the other hand, isotropic as there is no long range order. As there is no long range order at all. Okay, all right everybody. Now moving on, you know what, crystalline solids can also be classified into 4 different types. Okay, yes, so we understood what is solids, then we understood the solids can be divided into two types, that is crystalline and amorphous. Now crystalline solids can be classified into, and this chapter is mostly going to be more about crystalline solids, right? So there are 4 different types of crystalline solids: molecular solids, ionic solids, metallic solids, and finally you have the covalent or network solids. Yes, what are they called? Covalent or network solids. Okay, now time for us to dive deep into these. Okay, so what is molecular solids, guys? Solids in which the constituent particles are molecules. That is your molecular solids, right? Yes. So what did I say? I said that solids in which the constituent particles, this is not looking nice. Just a second. Solids in which molecules are called molecular solids. Make sense? Yes. Now molecular solids can be further divided into 3 types. Okay. Yes. So let's write that down also. molecular solids What are those? Number 1, polar molecular solids. Okay, yes. Then obviously if there is a polar molecular solids, you must have guessed it that there will also be a non-polar molecular solids. Yes, so number 2 is your non-polar molecular solids. And number 3, you have, what do you have? You have hydrogen bonding molecular solids or hydrogen bonded. Okay, let's call it hydrogen bonded molecular solids. Make sense, nonsense, guys? Yes, makes sense, everybody? Okay. Now see, why is it that non-polar solids, non-polar molecular solids even arise? Okay. In non-polar molecular solids, we know that electron is equally shared, right? Electron is shared equally between two elements, right? For example, BF3, we have studied about this. We have studied about this, if you remember. Even in the chemical bonding chapter in class 11, we have studied about this. If you haven't, please go and check it out. Yes, example for polar solids. Let me write the examples as well. Yes, let me write the example as well. Example for polar solid is your HF. Example for non-polar solid is your BF3. And hydrogen bonded molecular, you can take it as H2O. Okay, we will be studying about each one of them, don't worry. So what is non-polar? What is non-polar? You all know, right? It comprises of either atoms or molecules, yes, that are formed by non-polar covalent bonds. Correct? Yes. Comprises of, what does it comprise of? Non-polar molecular solids, they constitute of, yes, they are constitute, that means they are made up of either the atoms or the molecules formed by non-polar covalent bond. Yeah, non-polar covalent bond. Let me show you what is non-polar covalent bond. Do you see this? Do you see this? What is happening? Do you see this? What is happening? Now let me tell you something, that they are held by very weak dispersive force, which is also called as London force. What is London force? What is London force, guys? London force. London force is a temporary force. Okay. London force is a temporary force. It's not permanent at all. Yes. Now you know that the electrons are roaming around, isn't it? The electrons are free bird. They are roaming around wherever they want to. So what happens is at certain point they're roaming around. They're roaming around. See how they will all come here. See how they have all come here. All of them, all the black dots are here. The moment they have come here, here you get a negative charge, isn't it? Here you get a negative charge. The moment the electrons have come here, check it out, check it out. See, all the dots will come here. The moment all the black dots come here, there will be a temporary negative charge. The moment a temporary negative charge is here, now what will happen is in these two you will get positive charges here. Okay, positive charges will be here and they will get attracted. So there will be a bond that will be created between these. Okay, and it's a temporary bond. So that is what is called as London forces. Okay, that is what is called as London forces. So let's write it down then. Yes, what is non-polar? Non-polar basically constitutes of atoms or molecules formed by non-polar covalent bond. Okay, constitutes atoms or molecules, yes, atoms or molecules formed by non-polar covalent bond. non-polar covalent bond. Yes, and atoms or molecules, I have just told you London forces, right? So let's write that down also. The atoms or molecules, atoms or molecules are held together by weak dispersive force or London force. I have explained you London force as well, and London force is temporary, that I have told you, correct? So this is clear about non-polar molecular solids. I hope it is clear. Now let's go to the polar molecular polar molecular solids. Yes, I have taught you solutions, so I am constantly telling you polar molecular solvent. No, it's not solvent, solids. Yes. So here what is happening? Obviously, yeah, same definition. You can repeat it. Molecules are formed by polar covalent bonds. So let's write it down. Molecules are formed by polar covalent bonds. Do you remember that story that I told you? Yes, in my class 11 standard in the class 11 standard chemical bonding chapter, I've told you a story where, remember that me and my brother, we were both fighting for the remote. Yes, we were both fighting for the remote. There was a time when we both wanted to watch CID, and then I grew up and I wanted to hear all these English songs by Linkin Park and, you know, blah 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 and all of that, like Coldplay and all of that, right? So I wanted to hear this, and but that fellow was still young. He wanted to still watch CID. So we fought. Yes. Now whoever was stronger between us, certain times he was stronger. He could give me a punch and he could take the remote, and certain times I could pull his ears and I could take the remote. So whenever I pulled the remote, I took the electron. I pulled the electron closer towards my side. I was more electronegative, right? So what happened? There was a polar covalent bond created. He was angry, I was happy. You see, two equally opposite people bonded together by a family bond. That's your polar. Yes, that's a polar family. That's why polar siblings. Correct? Yes. So example, what is the example that we can take? HF. I told you, HF was an example. HCl. In case of HCl, what happens? In case of HCl, we see that Cl is more electronegative. Cl is more electronegative. Correct? So if Cl is more electronegative, what does Cl do? Cl pulls the electron closer to itself. Okay, Cl will pull the electrons closer to itself. Another example is SO2, SO2. Oxygen is more electronegative, so oxygen will pull the electron closer. So here what happens is molecules are held together by a relatively stronger dipole-dipole interaction. Dipole only, no? Two equally opposite charges separated by a distance. What is it? Dipole only, na? Exactly. Yeah. So let's write that down. Here what do we write? We write that molecules here are held together. Molecules are held together by dipole-dipole interactions which is relatively stronger. Alright, yes. So here you can see HF, how hydrogen has this electron, but this electron is also pulled by fluorine. So when fluorine is more electronegative, there will be a delta negative here, and here you will have a delta positive. Correcto? Right, everybody? Makes sense, nonsense? Makes sense, right? And then we finally come to hydrogen bonded molecular solids. Here what happens is you get to see a very strong hydrogen bonding that binds the molecules of such solids. Now, of course, when we are talking about H2O, we are not talking about H2O liquid. We are talking about ice. Yeah. Yes. So what do we write here? We write that here what is happening is strong hydrogen bonding binds the molecules of such solids. Yes. So molecules are bound together by strong hydrogen bonding. All right. Yes, you want to see a picture? Let me show you a picture. See, here is what happens. See, this H2O is a different molecule. This is a different molecule. Now, this oxygen, right? This oxygen will be bonded, or this hydrogen is bonded. So, this white ones are hydrogen. This hydrogen is bonded to this oxygen, right? This hydrogen is bonded to this oxygen, and that is your hydrogen bonding. That is your hydrogen bonding. Getting my point? Yes. So here also the molecular solids, they contain polar covalent bonds. Here also polar covalent bond is acting. Why polar? Oxygen is more electronegative. That's why it is able to pull the hydrogen, isn't it? Exactly. So here also what do we write? We write that molecular solids contain polar covalent bonds. Okay. Molecular solids contain polar covalent bonds. All right, everybody. Yes, understanding. Yes. Acha, by the way, what do you think? Are they conductors of electricity? See, we say that tap water is a conductor of electricity, but we are talking about H2O, just H2O. Will just H2O be conductor of electricity? No, Baba. They are all bonded. Where are the free electrons to take the charge? Where are the free electrons? Do you see any free electrons here? No. Do you see any mobile charge carriers here? No. So what are they? Non-conductors of electricity. What are these? They are non-conductors of electricity, or we can say that they are insulators. They are non-conductors of electricity. Okay, cool, everybody. Yes, understood. And yes, they become volatile liquids or soft solids under room temperature and pressure. That is something that you can skip it also. Okay. Now we come to ionic solids. Yes. So what are ionic solids? Solids in which constituent particles are ions. Easy peasy. Biryani tasty. Exactly. Yes. So what do we write? We write that solids, what did I say? Solids in which the constituent particles are ions. Okay. Solids in which the constituent particles are ions. Yes, okay, all right. How are they? Have you seen NaCl? They're hard, of course they are hard, right? But they are also brittle in nature. Yeah, they're hard, but they're also brittle in nature. And you will see that if they are in the solid state, right? In the solid states, they are electrical insulators. But in the molten state, they are good conductors. So what do we write here? We write that in the molten state, they are good conductors of electricity, whereas in solid state they are electrical insulators. Cool? Clear? Yes. Also, have you seen that? Have you observed? I don't know if you have observed, but they have really high melting point and boiling point. What do they have? They have a really high melting point and boiling point. High melting point and high boiling point. Got my point? High melting point and high boiling point, got my point. Anyway, so this is done. Now we come to metallic solids. What happens in metallic solids? In metallic solids, you get to see that metallic solids, you know that they can give away electrons very easily, right? They can give away electrons very easily, isn't it? So there is basically a sea of free electrons. They can very easily give away electrons. So there is a sea of electrons, yes, and you will see orderly collection of positive ions. So what did I say? Yes. What did I say? That they have sea of free electrons and there is orderly collection of positive ions. So positive ions are surrounded by sea of electrons and they are held together. Okay, and they are held together. So we can write that orderly collection of positive ions, yes, surrounded by, yes, surrounded by and held together by sea of free electrons. Now see, here is the word, here is your key word, okay? Free electrons. So because they have free electrons, you all know that they are what? High thermal and electrical conductivity. Everybody will agree with me, I guess. Yes, what do they have? They have very high electrical and thermal conductivity. Correct, isn't it? High electrical and thermal conductivity, correct or not? Right? They are ductile in nature. You have studied all of these from very young age. Ductile, they are malleable. Yes, they are lustrous. They are sonorous. Yes, you have all studied all of these. Correct? Yes. Correct. These are the properties of metallic solids. And finally, we come to the last type of solid, that is your covalent solid. Covalent solids, what will happen? Common sense. Tell me what will happen? There will be covalent bond, right? There will be covalent bond between two adjacent atoms. If there are two adjacent atoms, there is a covalent bond that exists, okay? So what do we write? We write that between two adjacent atoms, between two adjacent atoms, covalent bond exists. Covalent bond exists, okay? They are also hard and brittle. They have extremely high temperature, extremely high melting point, okay? Extremely high melting point. Talk about diamond, guys. Talk about diamond. Extremely high melting point, correct? Yes, all right, everybody. And they are obviously insulators because what they are bonded, right? They are insulators, electrical insulators. All right, makes sense, nonsense, everybody? Makes sense, right? So that means that till now, whatever we have studied, this is there in your NCERT book. Yes, if you want to check it out, you can check it out. So this is their types of solids. We have read about molecular solids, polar and non-polar, hydrogen bonded, ionic solids, metallic solids and covalent or network solids. Yes. Why network solids? Have you seen the structure of diamond? Doesn't it look like a cage? Doesn't it look like a network? It does look like a network, isn't it? So here in this case, you will also find the examples. For example, molecular solids, constituent particle is molecule. What is the bonding or attractive forces? Dispersion or London forces, which is what I taught you. Examples is Ar, CCl4, hydrogen, iodine, carbon dioxide. Physical nature is soft, electrical conductivity, insulator, melting point very low. When it comes to non-polar, yes, if in case of non-polar, what will you see? You will again see London forces. In case of polar, you will see dipole-dipole interactions, yes, HCl, SO2, soft, insulator and low. Hydrogen bonded. What is the type of bonding you will see? Of course, hydrogen bonding. Common sense, yeah. Yes, then you will see here H2O. Physical nature is hard. It is still an insulator. Melting point is low. We come to ionic solid. Constituent particle is ions. Here, of course, bacha, ion, positive and negative charge. What is the force? Electrostatic or Coulombic force. Yes. Examples are NaCl, MgO, ZnS, CaF2. Physical is hard but brittle. Here you will see insulators in solid state but conductors in molten state, and they are also conductors in aqueous solution, of course. Melting point is high. Metallic solids, positive ions in a sea of delocalized electrons. This is what I wrote, metallic bonding. Examples, iron, copper, gold, silver, magnesium, all of these hard but malleable and ductile. Conductors in solid state as well as molten state. Melting point fairly high, not too high but fairly high. Covalent or network solids, what is the constituent particle? Atoms. Bonding is covalent bonding. Example is SiO2 quartz, SiC, then carbon diamond. Yes, graphite also, physical nature is usually hard or it can be soft as well. Electrical conductivity, mostly they are insulators except graphite. Graphite is an exception. Graphite is a conductor and the melting point is very high. Okay. Alright. Now we have to understand crystal lattice. Crystal lattice, when we come to crystal lattice, you have to understand that basically it is nothing but a 3D arrangement of points in space. What did I say? A 3D arrangement of points in space, and that is called as a crystal lattice. Okay, so let's write it down. Yeah, let's write it down here. Okay. A three-dimensional arrangement of points in space, yes, of points in space is called as crystal lattice. Okay, that is your crystal lattice. Very easy, very peasy, right? Easy peasy biryani tasty. Okay. Alright, now do you know how many crystal lattices are possible? If I tell you, you'll be like, what, ma'am? Seriously? Yes. 14 possible 3D lattices. Yes, there are 14 possible 3D lattices and they are called as Bravais lattice. Okay. Yes, there are 14 possible 3D lattices, 14 3D possible lattices. Yes, and they are called as what? They are called as Bravais lattice. He was a mathematician. If you just want to see how he looks, this is how he looks. Yes. Now, each point in a lattice, you know what, let's draw a lattice here. Okay, let's try to draw a lattice here. Take a look at it. If I draw a lattice like this, let's draw a cube here first. And then let's draw another cube. Now see, these are the points here, right? These are the points, isn't it? Yes, guys? These are the points, isn't it? So what I'm saying is that each point that you see here, you know what, let me use another color so that you can understand it a little better. Let's use red here, okay? These points that you see, yes, what do they represent? What do they represent? What do you think? What do you think these are? These points that I'm showing here, they are called as lattice point or lattice site. And each of these points, they actually represent the constituent particle. What are the constituent particles? The atoms, the ions, the molecules, whatever is the constituent particles, they represent them. Okay, so let's write it down. Let us write it down. What did I say? I said that each point, yes, each point in a lattice is called as lattice point or lattice site. Yes, lattice site. Each of these point, okay, each point, once again I am writing each point, but it is going to be a different sentence, okay. Each point in a crystal lattice, what does it represent? I just told you. What does it represent? Yes, crystal lattice represents a one constituent particle, okay. It represents a constituent particle, all right. Now, take a look at the diagram here once again. Yes, take a look at this diagram. Do you see that I have joined these dots? I am joining these dots with straight lines. Why? So that the geometry can be brought out. Check it out. If I erase this, okay. Let's say that I erase this straight lines. Check it out here. What if I erase this, erase this, erase this, erase this, erase this. Now, can you understand what is the geometry of this? Can you understand that this is a cube? Not really, right? You cannot. So, exactly. Now can we understand that yes, we do need the straight lines. We need to join the lattice points so that the geometry of the lattice can be brought out, okay. So, let's just draw it again. Yeah. How is it? It's like this, I believe. Somewhat like this. That's how I drew it, I guess, if I'm not wrong. Yeah, that's how I drew it, correct? So, what did I say? The lattice points are joined together by straight lines. Let me write that down also, okay? Lattice points are joined together by straight lines to bring the geometry out. To bring the geometry, yes, to bring the geometry of the lattice. Now, if you want, you can write this down. Otherwise, I will be providing you with the note anyway in the Telegram channel. So, what you can do is just join the Telegram channel. You will be getting it, okay? Now, here is a term that is called as unit cell. Do you know what is unit cell? Unit cell is actually the smallest portion of a crystal lattice. Now, crystal lattice can be big, right? So, unit cell is basically, just like how you know the cell is the fundamental basic unit of our body, just like that, a unit cell is the smallest portion of crystal lattice which is repeated in different directions, and that generates the lattice. Let me show you a picture. So, this, my dear student, this red part or the pink part that you see, that is your unit cell. Whereas this part, this whole thing is basically the lattice, okay. So, let's write it down. What is a unit cell? Yeah, what is a unit cell? Unit cell is the smallest portion, of a crystal lattice. It is repeated in different directions to generate the lattice, okay. To generate the lattice, all right. Yes, now a unit cell, if you take a look at it, it is characterized, okay, like the properties. You understand that obviously there has to be properties when we are talking about something, isn't it? Just like a cell has a property, right? Like it has to be only this much is the measurement of the cell, right? It is supposed to do these bodily functions and all of that, right? properties, characterizations. We always do characterize certain things, isn't it? So very same way, we are also characterizing a crystal lattice. Not crystal lattice, we are characterizing a unit cell. How are we doing that? Okay, let's understand. Let's draw a cube here again. Let's draw a cube here again. Right? This is my cube. Now, obvious reasons, do you see that this is a side? Yes, this is a side. This is also a side, right? And exactly why we have different angles here, right? We have different angles, like this is an angle, this is an angle. Yes, yes, everybody. And we also have another angle that is basically this between C and A, right? So these are the 6 parameters that a unit cell has. A, B and C, these are the sides, the axis, yes, the axis of the cube, and the angles which are called as alpha, beta and gamma, okay? Alright, so what do we write here? We write that the unit cell is characterized by 6 parameters, okay? The unit cell is characterized characterized by 6 parameters. By 6 parameters. What are those? A, B, C, alpha, beta and gamma, okay? Alpha, beta, gamma, A, B, C, these are the parameters, 6 parameters of the crystal lattice. Now, obviously, we are going to talk about what is the difference, and we will be taking a look at the different types of crystal lattice, which is why the parameters are important. You will see, don't worry, okay? Now, different types of cubic unit lattices, right? These unit cells, they can be broadly classified into 2, okay? What are these? They can be broadly classified into 2, and number 1 is called as primitive and number 2 is called as centered. Centered can be further divided into 3, that is BCC, body centered, FCC, face centered, and ECC, that is end centered, or it is also called as base centered, okay? So these are the 3 different types of centered unit cell, and the primitive unit cell is right here. A simple cubic unit cell is basically the primitive unit cell, okay? All right. Now what happens in this case is, okay, in a simple cubic unit cell, basically what happens is atoms only are at the corners of each, okay, corners of the each unit cell. Basically, do I have anything to show you? I think so. I might have something, but let's see if we can pick it up, because I might be doing something that is not allowed here, but let's see. Alright guys, so do you see this? I might even get a shock, right? Yes, so like how you have 8 corners, 1, 2, 3 and 4, and back side also, if you imagine this, right? Back side also, if you imagine this, you will have another 8 corners. So atoms are basically taking these 8 corners, okay? Atoms are holding on to these 8 corners. Phew, did not get a shock of my life. Alright, amazing. So I hope you understand. Yeah, so that's a simple cubic unit cell where atoms are taking up the 8 corners of the unit cell, okay? And each atom is actually shared by 8 adjacent unit cell, okay? Each of this that you see, right, this that you see, here will be one, there will be another one here, there will be another one here, there will be another one here. Yes, so 8 adjacent unit cells are going to share this atom. All right, yes, okay. Now we come to body centered cubic unit cell. In case of body centered, basically cubic unit cell, what happens is, imagine that this is a unit cell. It's not a cube, of course, it's a cylindrical object, but imagine that this is a cube. If this is a cube, obviously at the 8 corners, 1, 2, 3, 4 and back side 5, 6, 7, 8, Yes, at the 8 corners, there will be atom. Apart from that, right at the center of the body, like this bulb, here will be another atom, okay? Yes, that's your body centered. Now, when we come to face centered, what happens is right here, okay? Imagine this is the remote here. This is the remote here. Right at the face here will also be an atom. Apart from the 8 corners, 1, 2, 3, 4, 5, 6, 7, 8. Apart from that, right at the face also you will have atom, right? Right at this face, right at this face, right at this face, right at this face. Yes, in all the faces, there will be 6 faces of the cube, isn't it? Yes, there are 6 faces of the cube. In all the 6 faces of the cube, there will be atoms, okay? There will be atoms that are occupying, okay? Got it, everybody? Yes, amazing. Now, let's take a look at the different types of primitive crystal cell, okay? There are 14 different types of primitive crystal system, by the way, my dear students. So, cubic is where the axis A, B, C are all equal to each other. A is equal to B is equal to C. All the sides, all the axes are similar. And guess what? Even the angles are very similar to each other. That is alpha, beta and gamma is also equal to 90 degree. Okay. Now, again, for cubic unit cell, you have 3 different types. What are those? Let's check it out. Yes, you have a primitive like this one. This is the primitive. Okay. This is your primitive cubic cell. Primitive cubic unit cell. Right here at the center of the body, you have a cell. That means this is your body-centered cubic cell. Okay. This is your body-centered cubic cell. All right. And this one, the last one, this is your face-centered cubic cell. Okay. This is your face-centered cubic cell, right? Do you see 1, 2, 3, 4, 5, 6? At the 6 faces, there are 6 atoms. Yes. Clear? Crystal clear? Got it? Now we go to the second part. The second one is called as tetragonal. Okay. The second one is called as tetragonal. You know what we will do? We will come back and we will do this again. Okay. Yes. So this is where say tetragonal, second one. This is the number 1 cubic. This is tetragonal. Tetragonal is where A is equal to B, but B is not equal to C. That is, one of the side is a little dissimilar. One of the side is not similar to the other two. A and B are equal, but C is not equal, which is why you are seeing that one side is a little longer. Can you see that one side is a little longer? Yes, exactly my point. So one of the side is a little longer, but all the angles are still 90 degree, by the way. Okay, all the angles, as you can see, are still 90 degree. Alpha, beta, gamma are still 90 degree. Tetragonal has another, yes, another type. So this is your primitive. Yes, this is your primitive tetragonal lattice. But apart from that, you also have a body centered. See, right here at the center of the body, do you see this blue color atom? Yes. So this is your body centered. All right. Yes. So my dear student, out of the 14 Brave lattice, we are done with 5. 3 from cubic, 2 from tetragonal. Okay. Now let's take a look at orthorhombic. Orthorhombic has 4 crystal lattices. Okay. This obviously is the primitive one, as you can see. Yes, orthorhombic is where the A side is not equal to the B side, is not equal to the C side. Yes, the angles still are 90 degree. Angles are still equal to each other, but the sides are not equal to each other. In the first one, cubic, we saw that A is equal to B is equal to C, alpha is equal to beta is equal to gamma is equal to 90 degree. Tetragonal, we saw that A is equal to B, not equal to C, but alpha, beta, gamma are still equal to 90 degree. In this case, alpha, beta, gamma are still equal to 90 degree, but now none of the sides are equal to each other. You know what? Let me show you this. Do you understand that this is your B, this side is your B, this is your C, and this is your A? So A is not equal to B, is not equal to C, and this is your orthorhombic. Yes, the AC remote is your orthorhombic shape. Yes, now in orthorhombic, this is your primitive where there is only 8 corners that are occupied by atoms. But apart from primitive, you also have end-centered or base-centered. In case of end-centered, do you see that this and this are not occupied? All the faces are not occupied. In face-centered and end-centered, the basic difference is In face centered, all the faces are covered, but in end centered, you only take two sides maximum, two faces, okay? Only the ends are occupied. So this is your end centered, right? Yes, then we come to body centered. See, right at the center you have an atom. Yes, so this is your body centered, okay? This is body centered. And finally, obviously, what is the other one? The last one is face centered. Of course, in face centered, you will also have 6 faces which are occupied by atoms. Okay, so how many are we done? 4 here, 3 plus 2, 5, 4, 9. 9 out of 14 are done. Okay, 9 out of 14 are done. Now let's take a look at hexagonal. Okay, in case of hexagonal, now what happens is, so in the last one we saw that A, B, C are not equal. Now once again we have come back to A and B are equal, but they are not equal to C. Okay, one of the side is different. Two sides are similar, one side is different. Okay, what did I say? Two sides similar, one side different. Okay, one side different. And what we will see this time is that two angles equal to 90 degree, that is alpha and beta, whereas the other angle, that is one angle is going to be equal to 120 degree, which is your gamma. So now do you understand? Yes? Are you understanding, everybody, what is happening? Now we have gotten back to two sides being equal, one side being different, two angles equal to 90 degree, one angle being equal to 120 degree. 10 completed. 4 more left, everybody. Now let's take a look at monoclinic. Okay, what happens in monoclinic? Monoclinic, what you have is alpha, none of the sides are equal to each other. All the sides are different from each other. Okay, all the sides are different from each other. But what is happening is, two of the angles are equal to 90 degree, but one of the angle is different. Okay, one of the angle is different. So this is your primitive monoclinic crystal lattice, and this is your end centered or base centered crystal lattice monoclinic. Okay, this is your end centered. There are only two types. Okay, there are only two types in case of monoclinic. Then we come to triclinic. Triclinic has, again, all the sides are not equal, just like this. All the sides are not equal, all the sides are not equal, but this time none of the angles are equal to 90 degree. None of the angles are equal to 90 degree, and this does not have any other type. There is only one type, that is your primitive. Okay, you only have the primitive kind of crystal lattice here, primitive type of crystal lattice here. None of the angles are equal to, none of the angles are equal to 90 degree. Okay, are equal to 90 degree. All of them are different. Getting my point? Last one, everybody. The last one is called as rhombohedral, where once again, now what is happening is, none of the angles are equal to 90 degree, but the sides are equal. The sides are equal to each other, but none of the angles are equal to 90 degree. However, the angles are equal to each other. Alpha, beta, gamma are equal, but it is not equal to 90 degree. What did I say? Angles are equal to each other. Okay, angles are equal to each other, but not equal to 90 degree. Okay, but not equal to 90 degree. Got it? This one also has only primitive kind, no other kind is available for rhombohedral. Okay, so rhombohedral and triclinic has only one type of each. And with this note, 14 different types of Bravais lattice is completed. Check it out, everybody. Check it out. All of these we have completed. You can see it here that cubic we have studied about primitive, face centered and body centered. There are 3 that we have studied. Tetragonal has a 2, that is primitive and body centered. Rhombohedral has only one, that is primitive. Orthorhombic has 4 types here: primitive, face-centered, body-centered and end-centered. 4 types we have studied for orthorhombic. Yes. Monoclinic we have 2, that is primitive and end-centered. Triclinic only 1, we have studied primitive, and hexagonal also has just 1. Okay, these are all the ones that we have studied right now. So a quick revision, you can check it out. In the case of cubic, we know that A, B, C, all the sides are equal to each other and angles alpha, beta, gamma is equal to 90 degree. Okay. In case of tetragonal, we have seen that A and B are equal to each other, which is not equal to C, but the angles are all equal to 90 degree. Rhombohedral, we know that A, B, C are all equal to each other, but alpha, beta, gamma are equal to each other, not equal to 90 degree. Okay. Orthorhombic, we see that A is not equal to B, which is not equal to C. None of the sides are equal to each other, but alpha, beta, gamma are still equal to 90 degree. In case of monoclinic, we have seen that again none of the sides are equal to each other. Alpha and gamma are 90 degree, beta is not 90 degree. Okay, beta is 120 degree. But no, beta is not equal to 90 degree. Beta is 120 degree in case of hexagonal. Triclinic, the sides are not at all equal to each other. The angles are also not at all equal to each other, not equal to 90 degree as well. So this is a cheat sheet which you can keep it right in front of your face. You can print this out or you can draw it on your own. Keep it in front of your face and take a look at it every single day. I promise you will understand all of these in a very small time. Okay. Alright. So these are all the things that we have studied. Yes, I'm going to skip this slide. This is also present in your NCERT. Basically, it has nothing much. The only thing that is new here is the examples. Example of cubic is NaCl, sodium chloride, copper and ZnS. Example of tetragonal is white tin or SnO2, TiO2, yes, CaSO4. Orthorhombic has the rhombic sulfur, BaSO4, that is barium sulfate and potassium nitrate. Okay. Then we come to hexagonal. Hexagonal has graphite, zinc oxide and CdS, cadmium sulfide. Okay. Rhombohedral has calcite, CaCO3 and cinnabar. Monoclinic example is sulfur and triclinic example is H3PO3 CuSO4.5H2. All of these are the examples. Okay. Alright. Now let's take a look at number of atoms per unit cell. So we have studied a lot, right? When we know that 8 corners are occupied by 8 different atoms. In case of body centered, there is one at the center. But how many atoms are we talking about? In each unit cell, how many atoms are we talking about? So look at this diagram, my dear student. This kind, the one that we draw usually, the one that is very easy for us to draw, this is called as an open structure because obviously it looks very khali, right? Very empty, all open, every side is open, it is looking like. So we call it open structure, okay? But actually, do you really think that's how the atoms are? Do you really think that the atoms are maintaining space like a one-hand distance? COVID chal raha, COVID. Do you really think they're going to do that? No, yeah. They don't stay like this. What actually they look like is this. This is how they look like. But it looks very confusing, right? Now, atoms are occupying their own space, but for us it is very confusing. We are like, we're not liking it. So what do? Now we have made something that is convenient for us just a little bit for us to understand, but kind of this is how the atom stays. So in case of a primitive cell, the simple cubic unit cell, actually what happens, do you remember what I told you? That 8 adjacent unit cells are sharing that one atom. So obviously that means that all the 8 corners that are, occupied by atoms is actually multiplied with 1 by 8. Because every corner is what? Every corner is 1 by 8th of one atom because it's shared by 8 adjacent cells, right? So what do? We say that it is 8 multiplied with 1 by 8 for a simple cubic unit cell. I'll show you the calculations also, don't worry about it. Very, very soon we are going to do that also, okay? Alright, so this is how the actual portions are occupied. This is the space filling center. This is how really the atoms look like. Actually, if you want to see it, okay, this is how the atoms occupy space, and this is just for our convenience because we think that this is very easy. Khula, all khali, all empty, right? So we call it open structure. Understood? Yes. Now we go to BCC. Okay, once again, see, this is how we draw it. There is one at the right, at the center. This is our body centered one. Yes, but do you really think that's how they are existing? Not at all. They are actually existing like this. But if you look at it, you will be like, oh my God, what is this? I don't think I can clear JEE with this. No, not possible. You will give up. But actually, they are like this. See, at the center, see, one of the atom is occupying the center, and once again 8 corners. So that will be what? 8 into 1 by 8. Yes. So basically, if we have to write number of atoms here, check it out, check it out, check it out here. Number of atoms, yes, number of atoms per BCC unit cell. Per BCC unit cell, what will it be? 8 multiplied with 1 by 8. Yes, do you remember? Because this is 1 by 8th of an atom. Yes, this is 1 by 8th of an atom. And this is shared by 8 adjacent unit cells, right? So, 8 multiplied with 1 by 8 plus there is 1 right at the center. Yes, so that means that we will write plus 1, which means that 1 plus 1 is equal to 2. That means in a body-centered cubic unit cell, there will always be 2 atom maximum, not more than that. 2 atoms maximum. Understood? Easy peasy biryani tasty? Yes? Making sense? Making sense? Great. Okay. Now we come to face-centered. Okay. In case of face-centered, once again, number of atoms that this corner part you have understood, right? Yes, 8 into 1 by 8. Correct? 8 into 1 by 8. Now plus, do you see how the faces are looking? See, this one has half, this one has half, the top one is half. Similarly, the bottom one will also have half. Just like this, here at the back side also there will be a half. That means 6 sides. 6 sides, they have all half face, half face, half face, half face, half face, half face. Yes. So, can I write 6 multiplied with half? Can I do that? I can, right? 6 multiplied with half, I can do that. So that means that number of atoms per FCC unit cell. How much is it? 8 multiplied with 8 and 8 multiplied with 1 by 8 and 6. Okay, so 2 into 3, 8 gone, cancel. So 1 plus 3. That means in FCC there are 4 number of atoms per unit cell. Making sense or nonsense, everybody? Make sense, nonsense? Yes? Yes? Getting it? Once again, you can check it. See, all these corners, 8 atoms. Yes? All these corners, 1 by 8th of 8 atoms. Okay? 1 by 8th of 8 atoms. And at the faces, you can see that half atoms are also present. So, what are we doing? 6 into half. So, 1 plus 3 is equal to 4. Clear hai? Clear hai? Clear hai? Now we come to end-centered or base-centered. End-centered is also called as base-centered. Please pay attention, everybody. This is going to be very important when you are calculating. Okay, when you are calculating, it's going to be very important. Also, we're going to do questions. We are going to do questions, by the way. So tell me, number of atoms per unit cell here. How much will we write? Number of atoms per unit cell is equal to, of course, 8 into multiplied with 1 by 8, that is for sure. But we also see that there are end-centered, there are 2 atoms here. But are they really 2? Are they really 2? No, half, just like that face-centered. So, it will be plus 2 multiplied with half. That means 8 cancel, 2 cancel, 1 plus 1 is equal to 2. Yes? So, end-centered and body-centered, both of them have what? 2 atoms per unit cell. Primitive unit cell, simple cubic unit cell has only 1 atom per unit cell. Okay? Alright. FCC has the highest. There is 4 atoms per unit cell. Alright, everybody? Yes, and end-centered has only 2. Now, shall we do a question? Let's take a look at the question. So, tell me how many space lattices are obtainable from the different crystal system? Okay, very easy, very peasy. Yes, very simple, very easy. I'm pretty sure that you can do it. Come on. Tell me, guys. Tell me. Are we done? This is very easy, right? Of course, the answer is 14. I kept telling you, right? We only know about, there are only 14 possible three-dimensional lattices known as Bravais lattice, okay? There are, okay, my sweater is disturbing, yeah. There are how many? There are only 14 possible Did I sleep a little less yesterday? Why am I making such horrible spelling mistakes? Yes, three-dimensional lattices known as Bravais lattice. Cool? Okay, all right then. Moving on. Yes, moving on. Next question. Tell me, in density, Z multiplied with capital M divided by A cube Na, what is Z here? Do you think Z is atomic number, or do you think Z is number of atoms per unit cell? By the way, you haven't done this question, I mean you haven't gone through the formula of this density. We will be doing it a little later. Don't worry about it, but just use your common sense and tell me, what do you think is it? Are we talking about atomic number by any chance in this chapter? Not at all, right? What are we talking about? Number of atoms per unit cell. So obviously it is number of atoms per unit cell. So in here Z is equal to number of atoms per unit cell. Okay, all right. What is capital M here? Capital M is molar mass. I hope you have watched the video of mole concept and stoichiometry. If not, please do watch it. It's there in the channel. Yes, it's there in the channel. I have only recorded it. Yes, capital M is molar mass. What is A? A is the side of a cube. Okay, A is the side of a cube. All right. Yes, and then finally, what is Na? Na is obviously nothing but, as you all know, Avogadro number. Make sense, everybody? This is your Avogadro number. Cool? Alrighty then. Moving on from here. Now tell me a question. Yeah, this is going to be important and fun. A compound that is formed by elements A and B crystallizes in cubic structure. Okay. Yes, A and B crystallize to form what? A and B crystallize to form your cubic structure. So primitive, we are saying. Right now we are talking about primitive. A atoms take up the corners of the cube. So if I have to draw it, basically I will draw it like this. Yes, these are my cube. This is my cube. So A atoms occupy the corners. So corner, 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 corner and corner and corner. 8 corners, right? Yes. B atoms are at the face center. B atoms are at the face center. So this and this. Is that right? Yes. B atoms are at the face center, right? Correct. So an atom at the corner of the cube contributes to the unit cell how much? Yes. How much does it contribute? How much does it contribute? Come on guys. You know it. Chalo, let's do this here, okay? So let's write it. An atom, yes, at the corner of the cube, learn to solve it, okay, of the cube contributes how much? Yes, 8 multiplied with 1 by 8. Yes, yes, do you remember? To the unit cell, all right? Yes, to the unit cell. Yes, to the unit cell. That means number of atoms in the unit cell, number of A atoms in the unit cell. Yes, so A is basically 1 because 8 and 8 will get cancelled, right? Now, an atom at the face, an atom at the face of the cube contributes 6 multiplied with half to the unit cell, right? Yes. So B atoms are basically 3, 2 and 6 will get cancelled, so 3. So what is the formula? They are asking for the formula. What do you think is the formula? Don't you think that the formula is A, B, 3, because we have just figured that A is equal to 1. As you can see, A is equal to 1, B is equal to 3. So it's going to be AB3. Makes sense? Yes, the formula is AB3. Correct? Great. Next question, everybody. Let's do it. In a monoclinic unit cell, monoclinic guys, monoclinic, not hexagonal, monoclinic has only one primitive kind. If you remember, the relation of sides and angles respectively are, in case of monoclinic, what happens? The sides are not equal to each other at all. Two of the angles are equal to 90 degree and the other angle is different. In case of hexagonal, it is 120. In case of monoclinic, it is just not equal to 90 degree, which means that our option C is correct. Makes sense? All the sides are not equal to each other. Beta and gamma is equal to 90 degree, which is not equal to alpha. Makes sense, everybody? Makes sense? Makes sense? Yes? Makes sense? Nonsense? Makes sense? Nonsense? Makes sense, right? Great. Okay. All right. Got it. One last question, then we will, I think, then we will solve something else, okay? Or should we do it a little later? What do you think? What do you think? You tell me. Should we do it a little later? No, let's do it. Let's do it. An element occurs in, I think questions are fun, right? Questions are going to be a little fun. Chalo, tell me. An element occurs in BCC structure with a cell edge of 288 picometer. The density of metal is 7.2 gram per centimeter cube. How many atom does 208 gram of the element contain? Do you think you will be able to do it? Because we are not done with the density formula yet. I think let's come back to this question, yeah? Let's come back to this question after some time. Here is another question that this also let's do it a little later because it is from the density formula, that Z into capital M divided by NA into A cube. Yeah, it's from that formula. Let's do it a little later because then we will be able to understand it much better. Now we come to packing. Acha, imagine what if we keep all these, unit cell that we're talking about. So all these while we were trying to understand them as the unit cells, we were considering them as cube, we are considering them as monoclinic, considering them as triclinic and all of that, right? Now let's imagine that these unit cells are goal, they are sphere, they are like a ball, okay? Let's consider them to be like a ball. And do I have any ball here? Oopsie, no, nothing. So basically what happens is, and what is packing? What is packing? Packing is basically how are they arranged in the solids, right? How are they arranged in the solids? Just like, this is a sort of packing too. How are the batteries arranged in this battery tray? This is also a packing, right? How are they arranged? How are they arranged? They're just one beside another, right? One beside another. Yes, so that's an arrangement. That's a packing too, okay? So in case of packing, there are three different types of packing that we have to see. One is the close packing in 1D. One is close packing in 2D and the last one is close packing in 3D, okay? Alright, so in case of 1D, that is you only have one axis, just one axis. If you have just one axis, how are you going to arrange? Let's say that I have to arrange these remotes, okay? I have this remote, I have this remote, right? Just one beside another, that's how I'm going to arrange, right? That's how I'm going to arrange, isn't it? So very similarly, you can see that here the spheres are also arranged, okay? The spheres are also arranged one beside another. Do I have any other option here? One beside another. Do I have any other option here? Nothing. None at all. Because I am supposed to take only one axis, one dimensional, right? So one axis, that's it, one beside another. That's how I'm going to take a look at it, okay? Now if I have to do packing in 2D, packing in 2-dimensional, now what I can do is, I have two options, right? I can do it like this, see, this was one beside another. Now what I can do is, I can keep one top of another, isn't it? Yes, I can do this, one top of another, I can keep it like this. Exactly my point. Exactly my point. So packing in 2D is basically done like, see, you will take this, just a second guys, let's take it again. So basically you will have, what just happened? Yes, this is one dimensional. Now what I can do is, I can put 1 1 1 1 1 1 on top of another. Yes, I can do this. Yes. Now see, both of them are similar. So this is called as AA type. Okay. Yes, this is called as AA type. But there is also a possibility of, just check it out. Have a look here. Have a look here, my dear students. Yes. But there is a possibility that I can put the spheres at the gap. Can I not? I can put them here at the gap. And now this time they are not looking very similar. Yes, they are not looking very similar. So what do I call them? This is my AB type. Okay, this is my AB type. Now check it out here. Do you see these are forming, how many atoms are surrounding each other? How many atoms are surrounding each other? Don't they form like a square kind of thing? They do, right? They do. One atom is surrounded by, here also there will be, okay, let's consider this. One atom, this one atom is surrounded by 1, 2, 3 and 4, right? Yes? 1, 2, 3, 4, isn't it? Yes, correct. Makes sense? Nonsense? Making sense, right? 1, 2, 3 and 4. Here also there will be 1, right? So 4 atoms. Yes. So what is this called as? This is called as coordination number. Okay. Coordination number in AA type, my dear student, is equal to 4. Make sense? And that's exactly what is written here. See? That's exactly what is written here. Alright? Yes. We will talk about that also. In case of, you can see it here. See? 2D square, from 2D square closed pack, you will see that coordination number is 4. We will talk about it. Now just check, see here what is happening. One atom is surrounded by 2 atoms. So here what is the coordination number? Coordination number here will be 2, isn't it? Yes. Coordination number will be equal to 2. Make sense? Yes. Right? Make sense? Surrounded just by 2 atoms, right? Okay. In case of this, in this case, what is it that you see? In this case, if I make another layer, let's just try to make some more layers, okay? Let's just try to make some more layer. Here we will do, here, 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 here and here. Now once again, add the gaps here, add the gaps here, add the gaps here, add the gaps here, okay? So this is your AB type, right? Here, do you see, let's consider this, okay? Let's consider this. How many atoms is this surrounded by? 1, 2, 3, 4, 5 and 6. Yes. So what is the coordination number in this case? The coordination number in this case also, does this look a little like a hexagon? This does look like a hexagon, isn't it? 6 sides. See, 1, 2, 3, 4, 5 and 6 sides. So coordination number is 6. Here, coordination number is equal to 6. Got it? Yes. Now let's take a look at packing in 3D. What is this? This is again from the same 2D, from that 2-dimensional. Yes, from that 2-dimensional, this is what? This lattice is AAA type, isn't it? This lattice has AAA type. Correct? Yes, this lattice has AAA type. Yes. This is your simple cubic lattice. Okay. This is from that unit cell, is the primitive unit cell. Correct? Making sense? In this case, do you see that this is a AB type, because the first layer is not matching with the second layer, third layer is not matching with the fourth layer. So what do we call it? We call it AB type. Getting my point? Easy peasy, nothing much here to understand, right? Nothing much here, right? Okay. Now, so this 3D packing, how are you doing the 3D packing? The 3D packing is obviously done from the 2D packing, right? Once you have kept one above the other, now what are you doing? You are just generating that, you are just repeating the unit cell, isn't it? You are repeating the unit cell from here to here, you are repeating the unit cell from here to here, repeating the unit cell this side, repeating the unit cell this side, repeating the unit cell this side. Yes, getting it? What are you doing? Unit cell, this remote, if you consider this to be unit cell, what are you doing? Repeating it this side, repeating it this side, repeating it this side, repeating it this side. Yes, you're basically repeating it in all directions. So what does it become? 3-dimensional. Yes. In this case also, this is your simple cubic close packing, where you can see that this is like a cube. Yes, and the second layer is placed exactly like the first layer. So what is it going to be? A arrangement. What is the coordination number? The coordination number here is 6. Yes, what is it? 6. Why? Because, okay, let's consider this atom. Okay, let's consider this. Do you see 1, 2, 3, 4, 5 and 6? Yes, it is surrounded by 6 atoms. Correct? 6 atoms. So we call it coordination number is 6 here. Okay. Yes. Now, if you see this, the first layer is not similar to the second layer. What are we going to call it? AB type. Yes. Yes. And the spheres in the first layer, they are not touching each other. The spheres are not touching each other. Do you see? Yes. The second layer is arranged in the holes, wherever there is a gap. This one and this one has a gap, right? This too has a gap. So right here you have placed the second layer. They are not touching each other. The first layer, these two are not touching each other. We have at the hole, the gap place, wherever there is a gap, that's where we have arranged the second layer. So what do we call it? We call it AB type. Yes. Now if you consider this atom, how many of these are surrounding? 1, 2, 3, 4, 5, 6. Then at the top also there will be 1, at the bottom also 1. So the coordination number is going to be 8. Yes, coordination number is going to be 8, right? Amazing. Understanding, everybody? Yes, this is your body-centered cubic close packing and this is your simple cubic close packing. Yes, it's in 3D now. It's in 3D. Body-centered, you remember, right? 8 atoms at the 8 corners, 1 at the center. That's what it is. That's what it is. Okay? All right? Yes. Now, what we can do is, now what if placing the second layer over the first layer? When you place the second layer over the first layer, yes, you get to see some void. What is void, my dear students? Void means empty space. Void means empty space. Okay, that means it's a gap. It's a place where there is nothing. Okay, all right, it's a place where there is nothing, empty space. Now, when you keep placing one layer above another, one layer above another, one layer above another, there is a possibility that you will get to see some empty spaces. Now, some of these empty spaces, okay, some of these empty spaces will be basically like, okay, imagine that there are 3 atoms like this, and right over here or right at the bottom, okay, right at that side, the other side, there is another atom. So this will look like a tetrahedron, yes, 4 sides it will look like, right? Because 1, 2, 3, and then that side you have another one. Are you getting my point? Yeah, getting my point? I do not have balls. I think, you know what, next time I teach them, I must get those colorful balls so that I can teach you this better. But you right now you just have to imagine. I'm so sorry. I wish I had something. I will get it. I will get it. Next time I promise I'll teach you with all sort of this. Okay. Yeah. Okay. So this will look like a tetrahedron. Okay. Now what is a possibility? There is also another possibility that if you see this looks confusing, but understand this. What if you have 3 here, and then right on top of this you have, let's say that you also have something like this. Now this will look like an octahedron because it has lot of sides. Yes, it looks like a flower here. Looks like a flower here, but this will look like an octahedron. Octahedral, yes. So one of this is called as octahedral void, and this is called as a tetrahedral void. Okay, this is called as a tetrahedral void. So the first layer where you are seeing that hexagonal closed packing layers, right? What was this hexagonal? See, this was hexagonal, not this one, sorry. Where did the hexagon? Yeah, this is your hexagonal close packing. This is your hexagonal close packing. Okay, all right. Yes. So first layer is your hexagonal closed pack layers. All right, and the second layer is formed by placing the spheres in the voids of the first layer. So you have done that. You have done that A B layering. You have a hexagonal packing. Now, at the bottom, what you are doing, wherever there are the gaps, that's where you are putting those, okay? That's where you are putting those. So, you will be getting a tetrahedral as well as octahedral void, okay? What will you be getting? You will be getting both tetrahedral as well as octahedral void, okay? It will be very easy if I just had those colorful balls. It will be very super simple, it will be. But right now, I'm very sorry, you just have to imagine with me, okay? But I promise I'll teach you this better, even in a better manner. Just stay tuned to this channel. With all the colorful balls, we will be doing it. Don't worry, okay? Now, this 3D close packing from 2D hexagonal close packing, placing the third layer over the tetrahedral void. So, whatever is the tetrahedral void you had, on top of that, yes, on top of that, if you place another layer, on top of that, if you place another layer, yes, this will also be called as hexagonal close packing. What will you call it? You will call it as HCP, where the coordination number now has increased to 12. Okay. So basically what you're doing, understanding, you have a layer like this. Yes, you have a layer like this, right? Okay, let's consider this is the layer that you have. At the gaps, at the voids, you have placed these many balls, right? Now here again there are gaps that have developed. So now on top of these gaps you are placing this. Yes, you are placing third layer over these tetrahedral void. Now you are getting a hexagonal close packing, and what is this type? AB type, because they are not matching with another. Yes, the tetrahedral void is converted now. Okay, see, the tetrahedral void is converted. What did you do? What did you do? On top of this, you have placed this. On top of the tetrahedral void, you have placed this. The coordination number has become 12, and this is your hexagonal close packing. Easy peasy. Yes. Now what are we doing is, what are we doing is, did I say converted? No, it is covered, okay? Did I say converted? It is covered. This is covered, okay? Yes. To cover the tetrahedral voids, you have placed this. Yes, all right. Now moving on. What is this called? This is called as CCP, cubic close packing, or this is also called, this can also be called as face-centered cubic arrangement. Okay. Once again, the coordination number is 12, but this time what are you doing? See, A is a hexagonal close packing. Yes, A is just like this. Just like this, you have placed A. Now what you have done is you have placed B. Okay, you have placed B. All right, you have placed B here. Now in this case, do you see that? So B, how you are doing is, see, first one you have B is like this. For C, what you have done is you have made it like this. This is ulta of this triangle, right? If I draw a triangle like this and if I draw a triangle like this, are these similar? Are these similar? They are, but they are in the opposite direction, isn't it? Of course, my right hand and my left hand are similar, but they are in the opposite directions, isn't it? So, are they matching? Are they exactly similar to each other? No, that's what we have done. So, we are calling it ABC type. Are you understanding? What are we calling it? We are calling it ABC. So, from here, when you look at it from here, you get to see only one ball here. But because of this one, you are getting to see two balls here. This layer and this layer look similar. Yes, this layer and this layer, the first layer and the fourth layer are looking similar. So ABC, that's how the 3D packing will be done. What are you doing here? In this case, you are covering the octahedral voids. You are covering the octahedral voids. Do you remember what I taught you here? See, what did I do? I drew 1, 2 and 3 circles like this. Then what I did was, with a different color, maybe with a different color, let's draw it. See. So this is like an octahedral void. Yeah, looks like a flower. That's what you did. You covered that here, and that is your ABC type of arrangement. Okay. All right, everybody, making sense, guys? Clear hai? Awesome. Moving on. So how many types of void are there? We have spoken about tetrahedral void. We have spoken about octahedral void. Are there only these two types of void? No. There is also a simple void, which is your cubic void. You make a cube. Whatever is at the center, what is it? Khali? Empty? Yes, that is your cubic void. Okay. Cubic void is formed because of the 8 spheres. Yes, 4 in the above plane, 4 in the below plane. Okay. Because of that, you will be getting an empty space. That will be your cubic void. Tetrahedral void is formed. Yes, tetrahedral void is formed when a sphere of the second layer is placed over a triangular void. Understand this? Understand this? See. If I draw 1, 2 and 3, what do you get? Do you see a triangle here? Do you see a triangle here? Yes, a triangle here. Yes, do you see a triangle here? Now, on top of these, if I draw another ball here, then what is this? This is called as a tetrahedral void. This is called as a tetrahedral void. Okay. All right. Yes. Then comes your octahedral void. What is octahedral void? Octahedral void is basically, check it out one more time, let me teach you this. This is basically 1, 2, 3. You have a triangle here, you have a triangle here, but we are not going to consider it. Rather, what are we going to do is, we are going to draw 1, 2 and 3 now. So, we have a triangle on top of a triangle. So now it looks like an octahedral. Yes, now it looks like an octahedral, basically like a star, like a flower, kind of looks a little different. Okay, all right. Yes, so you are basically, what are you doing? You are combining two triangle, but like this, two triangle like this. That's how you are doing it. So when you cover like this, it becomes an octahedral void. Now listen. So just some time back, we calculated how many number of atoms are there in each unit cell. How many voids are there? What about the khali space? What about the empty space? How many empty space are there? That also we have to find out. And then we will be able to understand that how actually does the material look like. So, the number of close packing spheres, if at all, the number of close packed spheres, if the number of atoms, number of spheres, what are the spheres? Spheres are basically atoms. So, if the number of spheres are n, then the number of octahedral voids are also n. Cool. If there are 6 number of spheres, octahedral voids created by those 6 will also be 6. Cool. Okay. Yes. But the number of tetrahedral voids generated, that is 2 times of the number of, yes, the number of spheres that are used. Let's say if there are 4 number of spheres we have used, that means that the number of tetrahedral void is going to be 2n, that is 2 multiplied with 4. Okay. Alright, getting my point? This please do memorize. There is no trick. Just spheres is equal to so, and then you can do so 2n. Son2 you can call. Son2. So spheres is equal to octahedral 2, then number of tetrahedral is your 2. Okay. Or so2 it will be. So2. So2. So spheres is equal to octahedral, tetrahedral is equal to 2. So sort 2. Okay. Alright. Yeah. That's it. Now, what are the location? Where are they found? Where do you think are they found? Yes. Where are these voids found? Where are these atoms found? Chalo, let's take a look at that. Okay. So, 1 tetrahedral void in each small cube and 8 tetrahedral voids in total. Okay. See, right in this place, you have, this is your unit cell. This is your unit cell, 1 unit cell. At 1 unit cell, you will have 1. Okay, you will have 1. There will be 1 tetrahedral void in each small cube. Okay, all right, yes, and there are 8 tetrahedral voids in total. Yes, so tetrahedral voids are always twice, isn't it? How many number of atoms are you seeing here? 1, 2, 3 and 4. How much is it going to be? Twice, right? So 2 into 4, 8. Remember? Remember this? Yes. So there will be 8 number of tetrahedral voids. Okay. Alright. Nothing. These 2 diagrams that you see, basically this diagram is a cutout of this. Okay. From here you have just cut out a piece and then you have kept it here. Okay. Alright everybody. Yes. Now in case of octahedral voids, where are the octahedral voids there? Octahedral, as you know, yes, it is going to be what? Equal. So octahedral voids at a body center of the cube is equal to 1 into 1, right? 1. It will be inside the unit cell, inside the whole unit cell, isn't it? Yes. So total octahedral voids will be what? Total octahedral voids is basically, it is going to be same number of spheres. Yes, same number of spheres. 1 octahedral void at the center of each of the 12 edges. If there are 12 edges, at the center you will have just 1 octahedral void. Okay, yes, because what is happening is the 12 edges, yes, 12 edges, then what are you doing? 12 edges are basically what? 12 edges are basically shared by 4 unit cell, 1, 2, 3, 4, shared by 4 unit cells. So what did you do? 1 by 4. So that means there are 3. Okay, total octahedral voids located at edge is 3. Total number of octahedral voids will be 4. Okay, yes, total number of octahedral voids will be 4. Understood or did not understand? Is this confusing? Let's explain this again. Okay, we are trying to figure out how many octahedral voids are there in an FCC lattice or CCP. CCP and FCC lattice are the same. Okay, face centered or cubic close packing, same thing. All right, just 2 different names. Okay, now in this case, 1 octahedral void is at the center of the cube. If this is the whole cube, then there is 1 octahedral void at the center of the cube. Okay, all right. Now this 1 octahedral void at the center is basically what? It is in between 12 edges. Yes, it is in between 12 edges, 12 sides basically, right? Yes, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? 12 edges, correct, right? Understanding this much? Great. Now, octahedral void at the body center, right at this center, how many do you have? You have 1, right? You have 1 here, as you can see. Now we are saying that from here also it will start, right? It will not be just 1 here. There will be octahedral void that is coming out from this. There will be octahedral void that is coming out from this. Octahedral void coming out from that side. Octahedral void coming out from that side. 1 is at the center. 1 is at the center. But from the sides also it is coming out. Take a look at it. Imagine if this is a cube here. This is 1 single cube here. 1 is at the center. But from this side there is a octahedral void. This side octahedral void. This side octahedral void. This side octahedral void. Right? Because this is not the only thing. It is also getting repeated here, right? It is also getting repeated here. It is also getting repeated here. Also getting repeated here. It's getting repeated, isn't it? So there are 4 which is coming out from the 4 sides. Yes. So what are we doing? 12 multiplied with 1 by 4. Why 12? Because there are 12 edges. 1, 2, 3, 4, 5. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 12 edges. So 12 multiplied with 1 by 4, yes, right? So that becomes 3, 3 plus this one, 3 plus the one that is already inside it. So that becomes 4. Now getting my point? Yes, I hope. Let's solve some questions and see if we can do it. Number of tetrahedral void in FCC unit cell. Tell me, how much is the tetrahedral void? Tetrahedral void is going to be twice. So that means it is going to be 8. Yes, that means it is going to be 8, isn't it? There are 2 tetrahedral voids on each body diagonal at 1 by 4 in the distance of each other. So in total, what will you get? 8 in FCC. Okay. Next question. How many octahedral voids are present on the edges of a FCC lattice? Edges. Octahedral voids present on the edges of FCC unit cell. 12. We just did it. 12. Wasn't it 12? We just did it, right? Yes. Great. It is asking edges, on the edges of a FCC unit cell. Edges. How many edges are there? 12. So 12 is the answer. Okay. Now let's try to figure out the formula of a compound. Okay. How do you calculate formula of a compound? So when you are calculating the formula of a compound, basically you have to understand that there are bigger ions. What are the bigger ions? The bigger ions are basically the ones that have negative charge. When they have extra electrons, what do they become? They become bigger, isn't it? Why? Because the effective nuclear charge decreases and the electrons are coming in. The atom, the nucleus is not able to look at the electrons, so they are spread apart. So what is this called? This is called as anions. Anions are bigger in nature. Alright, yes. And so what happens is, usually the bigger ions, they do the what? They take the corners. They take the close packed structure. Okay, they take the close packed structure. And the smaller ions, they occupy the voids. Obviously, the khali spaces are small, no? So they occupy the voids. Okay, the smaller ions, who are going to be the smaller ions? The cations, the positively charged ions. They have lost electrons, so now they have squeezed in, they have become smaller in size. Now that they have become smaller in size, they take the voids. Okay, yes, what did I say? Bigger ions take the close packing, the corners. Smaller ions, they take the voids. Okay, now the fraction of octahedral or tetrahedral voids that are occupied, that depends on the chemical formula of the compound, obviously. Yes, that depends on the chemical formula of the compound. So now let's do it, number of voids. I think we have just done it, but chalo, let me write that down again, just so that you are revising. So once again, let's write it down. Let me change the color. If the number of spheres are n, then the number of octahedral voids is equal to n. Yes, so let's write it down. If the number of spheres is equal to then the number of octahedral voids is also equal to n. Okay, alright. Yes, now what is the number of tetrahedral voids? Number of tetrahedral voids is going to be 2n. You all know it. Number of tetrahedral voids is equal to 2n. Please do remember it, okay? Yes, alright. And apart from this, you know that smaller ions, the cations, they take up the void, and the very small cation, they will take the tetrahedral voids, because the tetrahedral voids are even smaller, right? Chalo, let's write that down as well. I don't want you to miss out on anything, so let's write that down also. What did I say? I said that the smaller ions that is cations, what do? They take up the voids. Okay, very small cations take up the tetrahedral voids. Okay, alright. Yes, and the bigger ions, where do they go? The bigger ions, they take the closed packed structure. Anions are bigger in nature, right? The bigger ions, that is the anions, what do? Yes, they take up they take up the closed packed structure. Clear? Chalo, now let's solve some question. Yes, we are almost done. I think the last bit of it is your defects. That is what we are going to talk about. So, element A is every element of FCC. Atom B is present at every octahedral void. Atom C is present at 25% of tetrahedral void. Okay. Chalo, let's solve it. Atom A is every element of FCC, right? Atom A is every element of FCC. FCC has how many atoms? FCC has 4 atoms. So that means 4 atoms of A. 4 atoms of A. Now we have to basically adjoin everything that we have learnt till this time. Okay. Yes. Atom B is present at every octahedral void. Okay. Atom B is present at every octahedral void. Okay, octahedral void is basically how much? Whatever is the sphere, that is your octahedral void. So that means this is also 4 atoms. 4 atoms of B. Make sense? Yes, 4 atoms of B. Now, atom C is present. Atom C is present at 25% tetrahedral void. That means that first of all, tetrahedral voids are 2n. So 2 into 4, that is 2 multiplied with 4, because the formula is 2n, right? Yes, 2 into 4 with 25 divided by 100. Makes sense? Yes, making sense, everybody? So what can we do here? 4 and then 25, 4 25s are 100, 25, 25 cancel. So answer is equal to 2. Yes, answer is equal to 2. So what is the possible formula? The possible molecular formula, as you can see, is possible molecular formula is A is to B is to C, which is basically 4 is to 4 is to 2. Yes, that means what can we write? We can write it as A to B to C. Can this be the formula? Simple ratio we have taken. Instead of writing A4, B4, C2, we can simplify it to be 2 is to 2 is to 1, right? So that's what we have taken it, A2, B2 and C. Make sense? Yes, clear? Great. Moving on. Next question, everybody. Let's do it. Element B forms CCP structure. Okay. Element B forms CCP structure and A occupies half of the octahedral voids. A occupies half of the octahedral voids while oxygen atoms occupy all the tetrahedral voids. Okay. The structure of bimetallic oxide. Element B forms CCP structure. A occupies half of the octahedral voids. Okay. How do we solve it? Chalo, let's do this here. I will be needing a little more space, so I might have to go to the next page where the answer is written. Okay, chalo, let's do it. Yeah. So number of lattice points is always equal to number of octahedral voids. Yes. Which is equal to 1 by 2 of tetrahedral voids, right? Which is equal to 1 by 2 of tetrahedral voids in CCP. Am I right? Yes. All right. Now number of atoms of B. Element B forms CCP structure. Okay, so number of atoms of B, CCP structure, how many it is going to be? 4. Yes, CCP is 4. Yes, A occupies half of the octahedral voids. If number of atoms of B is 4, half of the octahedral voids, that means 2. Yes, yes. So, number of A is equal to 4 by 2, which is 2. Basically, answer is 2. Yes, right. Now, number of oxygen atoms. Number of oxygen atom occupy all the tetrahedral voids. So, all the tetrahedral voids, basically it is going to be 2 multiplied with 4, 2 into 4. 2 into 4 is equal to 8, right? So, what is our formula? Our formula comes up to be, for ratio A is to B is to C, is 4 is to 2 is to 8, which can be simplified as 2 is to 1 is to 4. That means it is A to B C 4, I think, or it will be A to BO4, not C. C is your oxygen, isn't it? C is any your oxygen. So, A to BO4, or you can, no, wait a second. Made a mistake. Sorry. I have interchanged it. Sorry. One second. Sorry. Very simple error. Yeah. So, what I have done is, see, A is 2, right? So, ABO is basically 2 is to 4 is to 8, right? Which I can simplify as that 1 is to 2 is to 4. That means it is AB2O4. That is your answer. AB2O4 is your option B. Yeah. AB2O4. Make sense? Sorry. Yeah. That oxygen, I mean, the A and B I have, adla badli. That is what happened. Chalo. Next question. Oh no, now let's do the density of unit cell. What is this density of unit cell, my dear students? Okay. Now the density of unit cell is basically, what is density? Density is mass by volume, right? Mass by volume, exactly. Correct, everybody? Yes. So how can we give, how can I write mass of unit cell? What will be my mass of unit cell? My mass of unit cell will basically be number of unit cell multiplied with mass of each atom, isn't it? So let's write it down. Mass of unit cell. What is mass of unit cell? Mass of unit cell is number of atoms in unit cell. Yes, number of atoms in unit cell. Yes, multiplied with what? Multiplied with mass of each atom. Mass of each atom. Yes, what can I call this? What is number of atoms in unit cell? That is equal to Z multiplied with mass of each atom, M. Make sense? Yes. What is Z? Z is number of atoms present in one unit cell. Yes, right. And what is M? M is the mass of a single atom, right? Yes. Now, what is mass of an atom that is present in one unit cell? Chalo, let's write that also. Mass, what did I say? Mass of an atom that is present in the unit cell, okay? Mass of an atom present in the unit cell. Present in the unit cell. What is it going to be? What is it? Small m, yes. So, small m is equal to, how do we calculate it? Mole concept, you remember mole concept? Yes. What do you do? Capital M divided by Avogadro number. Yes. What is m? M is your molar mass. M is your molar mass. And this is what? This is your Avogadro number. So basically my density now has become mass of unit cell. What is mass of unit cell? Z multiplied with M. Yes, this is equal to Z multiplied with M divided by, what is my volume? Volume is basically, volume is going to be obviously A cube. Yes, because A is the side. Yes, A cube will be the volume. Which means that now what is my A cube? A cube will be multiplied with Avogadro number, because this is what we just did, right? Yes. Now what if we do not know mass of an atom? If we do not know m, then what we can do? We can write it as Z is multiplied with capital M, that is molar mass, then A cube multiplied with Avogadro number, which is exactly what is written here. Isn't it? Yes. Makes sense, everybody? Got it? Clear? Everything is written on this thing. Okay. Everything is written here. Chalo. Moving on now, let's understand what is packing efficiency. What is packing efficiency? Packing efficiency is basically the percentage of total space that is filled by the particles. What is packing efficiency? The percentage of what did I say? Total space. Yes, the percentage of total space filled by the particles is called packing efficiency. Okay, all right. Now packing efficiency is different for different types of unit cell. Okay, for simple cubic cell, the packing fraction is only 52.4. Okay, the packing efficiency for body centered is 68% and the packing efficiency for face centered is only 74%. So basically this has the highest packing efficiency, that means very little space is left. In this case, much more space is left. Okay, this means that if it is less percentage, that means less amount of space is filled, more amount of space is just empty. Okay, once again, this is just a table that you can keep it in front of you, because there is a relationship between R and A. What is R? R is the radius. What is A? A is the S, right? What is R? Why is R there? Because remember, in a cube, we are basically fitting an atom which is round, which is sphere. So there will be radius, yes, and there will be a relationship between the radius and the edge, or radius and the axis. Okay? Alright, everybody? Makes sense? Nonsense? Alright? Great. Now let's take a look at the defect. What are the defects? Defects are basically the irregularities. See, all the time there is no guarantee that everything is going to be perfect, right? Yeah, there is no guarantee about it. So imperfections are always there. And if imperfections are there, that means that these imperfections or the irregularities in the crystal, they are called as defects. Okay, so let's write it down. Imperfections or irregularities. Yes, imperfections or irregularities in a crystal. In a crystal are called as defects. Okay. Are called as defects. Okay. Now, there can be two different types of defects. Okay, there are two different types of defects broadly classified as point defects and two is line defects. We are mostly going to talk about point defects, my dear students, okay, not line defects. Yes. Now, these point defects, they can be further classified as point defects are further classified as stoichiometric defects. Yes. Then there is Frankel defect, there is Schottky defect, and there is non-stoichiometric defect. So, classified as number 1, stoichiometric defect. Yes. Number 2 is No, actually, no. Stoichiometric defect has Frankel and Schottky defect. Sorry. Stoichiometric defect, then there is impurity defect. Yes, there is impurity defect. And finally, there is obviously non-stoichiometric defect. Yes, there is also non-stoichiometric defect. Okay, so these are the three different types of point defects. All right. So what is stoichiometric defect? You remember the chapter that we have done, mole concept and stoichiometry. What is stoichiometry? Stoichiometry is basically where the particular ratio is not disturbed at all. Yes, the particular measurements, they are not disturbed at all. So stoichiometry of the solid is not disturbed in these type of point defects. So let's write it down. Stoichiometry of the solid, okay, of the solid is not disturbed in these point defect. All right. Yes, that is what is stoichiometry. So that means if imagine that there is there is atom A and there is there is an atom type of A and there is an atom type of B. Both of them will be equal in number. Both of them will be equal in number. Okay. You can also call this as intrinsic defect or thermodynamic effect, because mostly what happens is when you heat an element or when you heat a solid, that's when these kind of stoichiometric defects arises. Okay. This stoichiometric defect is now divided into 4. Yes, stoichiometric defect is divided into 4. What are these? The first one is vacancy defect. Vacancy defect. Okay. Second one is what? Any idea? Yes, second one is interstitial defect. Yes. Third one is now what? Third one is Schottky defect. Yes. Schottky defect. And the last one is Frankel defect. Okay. All right. The last one is Frankel defect. Okay. Yes. Now what happens is, in case of vacancy defect, my dear student, can you understand that vacancy, that means an empty space is created. Yes. What is happening? When some of the lattice sites are vacant, yes, when some of the lattice sites are vacant, let's write it down, everybody. Yeah, writing down will definitely help you. Make the notes with me. Yes, vacancy defect. Chalo, let's make it for vacancy defect. What is vacancy defect? Yes, what is happening when some of the lattice sites are vacant and the crystal and the crystal is said to have vacancy defect, right? Some of the lattice sites, there were lattice sites, yes, and what happened is the crystal, the unit cell, they left from the site. When they left from the site, there is a vacancy that has been created. So that means that the solid has vacancy defect now. Yes, so let's write it down. When some of the lattice sites, okay, when some of the lattice site or lattice point, when some of the lattice sites are vacant, the solid has vacancy defect. Okay. Now in this case, are you thinking that the density will remain same? The density will remain same? No, the density will decrease, because the lattice point, the lattice site is vacant now. There was something supposed to be there, but it's not there. It left. Density has been decreased. But how come then that is stoichiometric defect? Stoichiometric defect, the ratio should not get disturbed, right? But how come we have a stoichiometric defect and we are saying that density decreases? That's because the number of, equal number of void and basically what will happen is, let's say that a cation left from its lattice point, right? Left from its lattice side, isn't it? If a cation left, now what will happen? Anion will also leave. So equal number of A and B will leave, and that is why the stoichiometry will remain as it is. Okay. Then what is interstitial? There is interstitial defect also that we are just speaking about, right? What is interstitial defect? What is interstitial defect, my dear student? When some constituent particles, they occupy an interstitial site. Interstitial site is basically, that's not where it was supposed to be. That's not where it was supposed to be. Yes, for example, let's say that here, yes, let's say that this is your interstitial site, okay? This is your interstitial site. Now this atom, what it did was, it just moved from here and it occupied this interstitial site. So that will be an interstitial defect. Understood? Yes. So let's write it down. When some constituent particles occupy an interstitial site. Now in this case, what happens to density? Density remains same, okay? In this case, density remains same, obviously. Yes, and here density decreases. Understood, everybody? Yes? Wow, my handwriting is looking so much better. Practice makes you perfect. I'm telling you guys. This is live exhibit. My handwriting was super, super ugly in the beginning. I mean, seriously. I used to write on the board and it used to look like puke. And I always used to see other teachers handwriting and oh my god, they used to write so beautifully. But see, look at this. Now that I'm practicing more and more, I want to write on the board. It is getting better. Do you see it or not? Yes. Please, yeah, pat on my shoulder. Even if you are not saying that my handwriting is good or not, I am going to definitely, be your own cheerleader. You should also celebrate your effort. Chalo. Moving on. Now let's take a look at Schottky and Frankel defect. Okay. What happens in Schottky and Frankel defect? Understand. Yes. In this case, what is happening is equal number of cations and anions are missing, leaving behind a pair of holes. Let's write it down. Equal number of anions and cations. What do they do? Anions and cations are missing, okay? Equal number of anions and cations are missing, leaving behind what do they leave behind, guys? What do they leave behind? I just told you. Leaving behind a pair of holes. Cool. Okay. What about Frankel defect then? It is created when an ion leaves its site and occupies an interstitial site. It leaves its site and it goes and occupies an interstitial site. Okay. Yes. In case of Frankel defect, what happens here? Yes. How do we write it out? It is created when an ion leaves its own site and occupies an interstitial site. Got it? Yes? Okay. In this case, do you think that density will decrease? Of course, density decreases here. Yes? Now, what happens in Frankel defect? Do you think density will decrease? No, density remains unchanged. Okay? Yes? Now, what will happen? Coordination number. What about coordination number? Coordination number is high here. Alright, what happens to this? Coordination number is low here, okay? Okay, alright. What else? Radius ratio is not far below unity. You know what? Let that go, okay? These differences, do you understand? Yes, these differences, do you understand? Yes. Radius ratio is low here, radius ratio is not far below unity. Cation and anion, they don't differ much in size, basically, that's what they mean. Here cation and anion, they differ in size much, okay. These are electrically neutral here, both of them will be electrically neutral, obviously. Yes, these are electrically neutral here, and this is also electrically neutral. Right, this is also electrically neutral. Yes, examples. Let's write the examples. Here the examples are basically NaCl. Yes, NaCl is an example here. KBr. KBr is an example. What else? What else? What else? CaCl is also an example. Yes, all right. Here what are the examples? Examples are ZnS. Yes, apart from ZnS, AgBr, AgCl, and etc. Okay, all right. Yes, in fact, AgBr is actually an example of both. AgBr shows both Frankel and Schottky defect. Acha, one more thing. In case of the vacancy defect, I told you, I think somewhere I had told you that when some of the lattice sites are vacant, the solid has a vacancy defect. Here I told you that the amount of cations and anions are leaving are same, right? No, that's not the case. Sorry. Here what happens is basically when, let's say that this happens mostly in metals, right? What is happening is, do you know that metals, they lose some electrons and they become a cation, okay? They lose some electrons and they become a cation. Now, one of the cation has left. Let's say that one of the cation has just left its place, okay? Now, when it has left its place, you are thinking that there is a vacancy, so an anion will come. No, anion is not coming. I just told you that just some time back it lost some electrons to become an anion, right? Those electrons, they come and take the space. Those electrons, they come and take the space. So, the stoichiometry remains the same, okay? The stoichiometry remains the same, alright? So, these are the differences. Now, let's talk about impurity defect. In case of impurity defect, as you are understanding, common sense only, yes, what is it saying? Foreign atoms replace some of the atoms making up the solid, okay? Foreign atoms what do? Replace some of the atoms. Yes, foreign atoms replace some of the atoms making up the solid. Yes, replace some of the atoms that are making up the solid, okay? That are making up the solid. Yes, crystal clear everybody? Great. Moving on. Then we finally come to non-stoichiometry defect. What is non-stoichiometry defect? This type basically, from the name itself you can understand, right, what is happening. They disturb the stoichiometry of the crystalline substance, okay. They disturb the stoichiometry of the crystalline substance. They disturb the stoichiometry of the crystalline substance, okay. And in this case also, the electrical neutrality is still maintained, by the way, okay. The electrical neutrality is still maintained. It cannot be not electrically neutral, right? Electrical neutrality is still maintained. Get my point? Okay. All right. Yes. Now, what is happening is, how come I have, acha. So basically this is an example. How come I have these two slides? I have no idea, but I think that must have been a mistake from my end. So if you have ZNO here, what will happen is when you heat ZNO, it forms a Zn2 plus cation, right? Yes, and what happens is it also has 2 electrons. Do you see? There is also 2 electrons that it is giving away. Sides and they have went. So there is a vacancy that is created. Yes, negative ion is missing from the lattice side. Yes, what is negative ion? Anion only, right? So the anion, they got up and they left their space. Yes. What have they left? They have left a vacant chair. Yes, they have left a vacant chair. For example, you must have seen a lot of these IFA awards and all of these places where they have a seat with the name Amir Khan, but Amir Khan does not come. Nobody can go and sit in Amir Khan's place also. What is that? There is a vacant space. Yes, there is a vacant space. So anionic sites occupied by unpaired electrons are called the F centers, and it is mostly shown in NaCl. Yes. Now this can also happen. The metal excess defect can also happen because of cationic vacancies. Yes, because of presence of extra cation also it can happen. Zinc oxide can heating can show this. Yes, excess zinc 2 plus ions, they move to the interstitial sites and the electrons to neighboring interstitial sites. There is also metal deficiency. What is metal deficiency? Less amount of metal, Baba. Common sense, right? It contains less amount of metal. Example is Fe 0.950. Some Fe2 plus cations are missing and the loss of positive charge is made up by required number of Fe3 plus ion. Alright. With this note, the chapter is almost over, guys. There are some types of ionic crystals which I have mentioned. Nothing much, but just go through them once and just remember some of the examples. Okay, just go through them once and just remember some of the examples. And there are some questions which I want you all to do as a homework. All right. Yes, please do this as a homework. They are very easy, very simple questions. I'm just going to go through them. Yes, basically there are just 1 or 2 questions that I've left you, that I'm leaving you with. With this note, thank you so much. I hope that you have understood the whole chapter, but like I said, I promise I will bring you another session of this chapter where we are going to understand all the octahedral and the tetrahedral and the cubic voids even better. All right. With this note, tara bye bye. I'll see you very soon. All the very best and lots of love. See ya.